Hi everyone, have you ever wondered how a country's population changed over time? In this presentation, we will explore how mathematics can help us understanding population growth in Ecuador. For task 1, we focus on applying first-order differential equation to model the population growth from year 1980 to 2000. We use the Malthusian model to determine how the population increased over time. The model is represented by the equation dp over dt equals to kp, showing that the rate of growth is proportional to the current population. By using this model, we can analyze trends and gain insight into the factors that influence population growth, such as economic condition, migration, and government policies.
Now, I will be presenting the population growth of Ecuador from 1980 to 2000. Based on the data, Ecuador population shows a steady and continuous increase over these 10 years. In 1980, the population was approximately 8.16 million people. Each year, the population grew by around 200,000 to 300,000 people, indicating a stable growth rate. By 1990, the population has reached about 10.47 million, showing a significant increase of over 2 million people in just one decade. The growth trend continues throughout the 1990s, and by the year 2000, the population rose to approximately 12.69 million. Overall, this means Ecuador's population increased by more than 4.5 million people over the 10-year period. In conclusion, the data shows that Ecuador experienced consistent population growth from 1980 to 2000 without any decline, indicating a stable and developing population over time.
Now, I will explain step 2, which is forming the mathematical model. So basically, we need to find the particular solution. We let Pt represent the population at time t, where t is measured in years. We assume the rate of population growth is proportional to the population itself. So, we write differential equation as dp divided by dt equals to kp. Next, we have to separate the variables, dp in the left side and dt in the right side. Then we can integrate both sides, and the answer is ln modulus p equals to kt plus c. To remove the natural logarithm, we need to exponentiate both sides, and we will get p equals to 8e power of kt. This is our general solution, where a is a constant. Now, we use the initial condition at t equals to 0 is year 1980. In the year 1980, the population is 8,165,877. So, our A will equal to 8,165,877. Next, we find the value of K by using the data from 1981. So, in the year of 1981, population is 8386910. After substituting and solving, we can get K equals to 0.0267. So, the particular solution will become PP equals to 8,165,877 e to the power of 0.0267 t. Next, I will explain step 3, which is using the particular solution in the step 2. We use the particular solution to predict the population in 2001. We calculate t equals to 2001 minus 1980 equals to 31. Then, we substitute t equals to 31 into the equation. The predicted population in 2001 is approximately 14.3 million. This shows how exponential growth can significantly increase population over time.
Now, for step 4, we are predicting the population in the year 1979. First, we define our time variable t. Since our reference year is 1980, we calculate t equals to 1979 minus 1980, which gives us t equals to negative 1. Next, we substitute this value into our formula, which is pt equals to 8,165,877 e to the power of 0.0267t. So, we evaluate p equals to negative 1 by replacing t with negative 1 into the formula. After calculating, we get approximately the value of 795,0733. This means the predicted population for 1979 in Ecuador is about 7.95 million people.
This graph illustrates how population changes over time using two different models. On the horizontal axis, we have the year, while the vertical axis represents the population size. In the first graph, we can observe that an exponential growth pattern. At the beginning, the population increases very slowly and appears almost constant. However, as time progresses, the curve becomes steeper, showing a rapid increase in population. This graph indicates that the growth rate is not constant, but instead increases over time. This type of growth is typical in situations where resources are sufficient and the population continues to expand without significant limitation. In the second graph, we see that a comparison between a linear model and actual population data. The red straight line represents a linear growth model where the population increases at a constant rate. Meanwhile, the blue dot represents the actual data collected over time. Initially, the data points are quite close to the linear model, suggesting that it is a reasonable approximation. However, as time goes on, the data begins to deviate from the straight line, showing that the real population growth is faster than predicted. In conclusion, this graph demonstrates that population growth is better represented by an exponential model rather than a linear one, especially over a longer period of time.
Now, I will present the analysis of our result by answering question 1 and question 2. For question 1, we compare the values obtained from the particular solution with the actual population data. At the starting point, which is in the year 1980, the calculated value is exactly the same as the actual value, which is 8,165,877. This gives a percentage error of 0%, showing that our model fits perfectly at the initial condition. However, when we look at the year 2000, which is 20 years later, the calculated population is 30,928,876, while the actual population is 12,869,206. This results in a percentage error of about 9.77%, which shows a noticeable difference between the model and the real data. And we calculated the percentage error using the formula percentage error equals the absolute difference between the actual and calculated values divided by the actual value and multiplied by 100%. Our results show that the error increases over time from 0% in 1980 to 9.77% in 2000 and will be later discussed in the next slide.
Now, let's move on with the discussion. Let us address on why are the differences between the actual population values we observed and the values we calculated. The difference is because the model assumes a constant growth rate. However, in reality, population growth in Ecuador does not follow a perfectly consistent pattern. It is influenced by several factors such as changes in birth rates, death rates, and migration over time. These variations cause the calculated values to differ from the actual population data. If we look back at the past, population growth in Ecuador was mainly influenced by improvements in healthcare, which reduced death rates. This was paired naturally with high birth rates. Not to mention, economic development provided stability needed for families to expand, thus contributing to a steady increase in population. Turning to present and future, population growth may be affected by different factors such as advancement in medical technology that continue to shift death rates downward. At the same time, urbanization has increased, with more people moving to cities for better opportunities. Economic conditions and environmental factors, such as climate change, may also impact population growth. However, the growth rate has become more slower due to higher education levels, especially among women, that increase awareness of family planning. Overall, population growth is shaped by a combination of social, economic, and environmental factors, which makes it difficult for a simple mathematical model to fully represent real-world changes.
In conclusion, the 𝚗𝚊𝚍 model provides a clear and effective way to understand Ecuador's population growth. By comparing the predicted values from the model with actual data, we observe small differences with low percentage error, mainly due to real-world factors such as economic condition, migration, and government policies. Despite its limitation, the model offers a strong mathematical foundation to study population trends. Overall, this study demonstrates how differential equation can be applied to the real-life problem and provides a useful tool for predicting population change in Ecuador over time. Now, that's all from us. Thank you.